All right, well, welcome back. Seems like just yesterday we were talking. Actually, it was about 20 minutes ago that I finished up the last lecture. Do not ask me what I've done for my spring break. You've heard it. You've heard it all. Okay, let's get started. So, what we're going to do today is talk about lenses. Very similar kind of optical component to mirrors. We're going to find a lot of parallels. Even though at the basis there's something very different about them. That mirrors are taking advantage of reflection and the reflection of light at surfaces. Lenses are taking advantage of refraction and the refraction of light as it moves from one material to another. Another big difference is that mirrors have one surface, lenses have two. And so where mirrors have one focal point, lenses have two focal points on either side. We'll talk about that very shortly. All right, so lenses today. Let's start with a question. So imagine a lighthouse, and thinking about what a lighthouse does and what it's there for, what kind of lenses should you use in a lighthouse? So we've learned about two different kinds of lenses. Which one should be used in a lighthouse, or is neither one appropriate? So, as usual, pause the lecture, go to the quiz, and answer the question. Okay, so what kind of lens would you want to use in a lighthouse? Well, you certainly don't want to use a diverging lens. Now, a diverging lens would increase the way in which light gets spread. It would make the light more diffuse. Well, that's not what you want to do with a lighthouse. You want to make sure that people see it. You want to have usually a beam that sweeps out. In fact, you want to use a converging lens. You want to take a bulb or some other source of light, which is radiating light in all directions, and you want to gather all of that light, take it all, and put it into a single beam. You want to focus it. And that's what a converging lens can do. Not always, but under certain circumstances, a converging lens can take light, gather it up, and focus it. It's actually very much like what a concave mirror can do. And we'll see this parallel work itself out in a number of different ways. That converging lenses are very much like concave mirrors, and diverging lenses are very much like convex mirrors. All right, so let's move on. Turns out these are the two mirrors we're going to talk about, but there are many, lenses. There are many other kinds of lenses out there. Lenses have two surfaces, and those two surfaces can vary independently in terms of their curvature. The key about lenses is what happens when light hits that interface. And that, just like the case of mirrors, is going to be about the direction of the normal at that point. By varying the curvature, you vary the way in which the normal changes over the face of the lens, and you vary the way in which light is going to interact with that lens. Because you have two surfaces in lenses, they actually are a little bit more flexible than mirrors. Now, the two here that we're going to focus on in this class are the converging lens right here and the diverging lens. And you notice they have similar shapes, very symmetrical shapes, kind of inverse shapes. I do want to warn you about this. Sometimes if you go online or if you see other things, you will see these things referred to as biconvex and biconcave. So, and I don't want to go into this too much because I don't want it to get stuck in anyone's head, but if you look at the diverging lens, you could imagine that you could call it a biconcave lens because it's got a little cave on either side. The problem with that is the diverging lens acts like a convex mirror, not like a concave mirror. The shape might look like a concave mirror, but it actually acts like a convex lens. And so that's why I would discourage you from having any connection between the words you use to describe mirrors and the words you use to describe lenses. I think it's easiest and least confusing to stick with converging lenses, diverging lenses, convex mirrors, concave mirrors. And that's what I will do as I talk to you about these things. All right, so let's think about what happens when we have to use our lens equation. We have our equation that we used for mirrors, 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length of the optical element we're using. Works for lenses just like it works for mirrors. And that means we have sign conventions. We saw the first part of this in the last lecture. The second part looks very familiar. And this again takes advantage of the similarity between a concave mirror and a converging lens, and between a convex mirror and a diverging lens. Same rules about the focal length. So the focal length for a converging lens is always positive. It's really important to plug it in that way in the equation. The focal length for a diverging lens is always negative. It's very important not to drop that negative sign. It's going to have enormous repercussions. If you drop the negative sign, you're not going to get the right answer. Now, there are also some sign conventions for image distance and object distance. These are a little bit different than the ones you have for mirrors, because for a mirror, light bounces off. For a lens, light moves through. And it turns out then that we reverse the signs we attribute to image distances. So again, just like last time, only positive object distances. We're not going to worry about any negative object distances. Images that are formed on the other side of the mirror, on the far side of the mirror from the object, are going to have positive image distances. These are real images. Images that are formed on the same side as the object are going to have negative image distances. These are virtual images. It has a lot to do with you and how you are looking. In a lens, we assume you're always on this side of the lens looking. And so you have direct access to this side. Those objects are real for you. In a mirror, you're looking, so here's our mirror, you're looking from over here, because you can't look at anything from behind the mirror. So you have direct access to things over here. Those are our real images. So this is going to take a little getting used to, a little bit of practice. Just understand that there are these sign conventions. They are critical, and they will affect the answers that you get very dramatically. Okay. So let's think about what happens to light that goes through a lens. So imagine we have a lens here. It's a converging lens. It's got the shape of a converging lens. And let's say I have object A, which is radiating some amount of light. Now, I'm going to draw two rays here, but it's important to note that A could and probably is radiating light in all directions, even in here. I'm just picking out two rays to look at. Just like with our three principal rays, I'm just going to pick out a couple of rays and not worry too much about the others. I just have to do a quick thing here. All right. Sorry about that. I had to make sure that the microphone was on because I have done this and the microphone's not been on, and that's been a very disappointing. All right. So this object A is giving off light in all directions. It hits this converging lens. What's going to happen to it? Well, what does a converging lens do? It bends light in toward the principal axis. It converges that light. So in fact, I could conceivably get a real image over here. I could have those beams of light converge on the far side of the lens, create an image of this object that I could, say, project on a screen or probably see if I were looking at it. Now, let's imagine I move this object closer to position B. So I'm moving my object from A to B. It's still radiating light in all directions. What's going to happen? Well, here I'm going to pick up my two rays again, two particular rays of all the ones that are coming off this object. Let's say they hit the same places that the first rays hit. They're also going to be bent. So in this case, the act of passing through the lens bent the rays inward, in toward the principal axis. That's going to happen again. But notice that the rays now hitting the lens are hitting it at a much steeper angle. The lens can only bend light so much. It has its limits. And so it can't bend the light enough at position B in order to focus it anymore. The light is not converging. It's just going out parallel and straight. Notice, if we reverse that ray diagram, which we can do, and had the green arrows point the other direction, that would be a picture of light coming in from a distant source, hitting a converging lens, and ending up at the focal point. So point B, where our object is in the second step here, is actually the focal point, or a focal point of the lens. It turns out there's another focal point on the other side of the lens at the same distance from the lens. So if I have a focal point over here, I have a focal point over there. Again, because lenses have two sides to them. And if I had light coming in from the left side parallel to the principal axis from a very distant source, all that light would be bent enough so that it would converge on the focal point. Once I start moving that object closer, those rays hit the lens at a steeper and steeper and steeper angle. The lens can only bend them so much, and I get to this point of B where it can only bend the rays to make them come out straight. Now, I could move the object closer. What's going to happen then? Well, now I have my object at C. Notice those rays are hitting the lens at an incredibly steep angle. The lens can't even bend them enough to get them to go straight. They're still going to be diverging from one another. They're still going to be going outward. So here the lens has been able to bend them about the same amount, but because the rays started out so steeply, it can't make those rays converge on the other side of the lens. There's just no way to do that. Now, what this shows us is a kind of sequence of events, that we have an object that's outside, so object at point A, this is outside the focal point of the lens. That will get us real objects. Whoops. If we have an object far enough away from the lens is able to bend objects and bend rays enough to reconverge those rays on the far side of the lens and create a real object. If we have an object that's inside the focal distance or the focal length, the rays are hitting the lens much too steeply to be bent and converged on the other side. What we're going to end up with is a virtual object. The rays are still coming apart here. They're still diverging, just not from the actual object. It's from an image of the object. Okay, hopefully this helps to make some sense of what's going on with lenses and why it is that converging lenses can actually create both real and virtual images. It has everything to do with how far or close the object is to the lens. The lens can only bend the light so much. If you're too close, it can't bend the light enough to get it to converge and create a real image. All right, well, let's look a little bit more closely at lenses, how lenses work, what happens at the interfaces of the two faces of the lens. So here we have two different shapes of lenses, both converging. One is thicker in its middle than the other. Here's a question for you. Which of these do you think will bend light more? So if I pass, let's say, a beam of light through each of these lenses, which one will bend that beam of light more? Which one will converge it more quickly? So stop the quiz. Stop the lecture, go to the quiz, answer the question, and come back and we'll talk about it. Okay, so let's see what's going on. The question is, what's happening at each of these interfaces? At each of the faces of the lens. So let's look at lens A. I'm going to have a normal, so the light hits the lens. At that position, there is a normal to that surface. The normal is at an angle because the surface is curved. I have my light coming in. I guess I'll switch to a black ink. I've got some angle of incidence. I'm going to have some angle of refraction. That angle of refraction is going to be a smaller angle with respect to the normal. How do I know? Well, let's say the lens is made of glass, and out here we have air. I can write Snell's law that theta, in this case, let's say theta air sine of the incident angle is equal to theta glass. What am I doing? Oh, if only I had all of you here to stop me. Then everything would be okay. So we're talking about indices of refraction, not thetas. So this is the air. So my Snell's law, something just didn't look right. Air, and then the incident angle that's in the air, in glass, and the refracted angle inside the lens. So this is going to be 1. This is going to be bigger than 1. Any material we make a lens out of will have an index of refraction larger than 1, which means that if n is larger, then the angle here, the angle of refraction, will have to be smaller than the angle of incidence in order to balance everything out in the equation. So what that means is this light, this beam, is going to bend inward toward the normal. And the normal is in such a way that that means bending toward the principal axis. Now, that beam will then go through the lens and hit the other side, where I have a different normal at a different angle. Now I have, and this is getting small, but I have an angle of incidence here. Now I'm going from a larger n to a smaller n. When I do that, I actually have a greater angle of refraction. So now, in this case, I have n glass sine of the angle of incidence, and air sine of the angle of refraction. So this is at face 1, this is at face 2. Because this is larger, this will be smaller. The angle of incidence will be smaller than the angle of refraction. So at both faces, the beam is bent toward, this beam coming in parallel to the principal axis is bent down toward the principal axis. Well, let's look at lens B. Turns out lens B has such a shallow curvature, the normals are almost flat. They're almost horizontal. So there's not actually going to be much bending happening. The angle of incidence is going to be really close to 0. That means the angle of refraction is going to be pretty close to 0. So I will get some bending in lens B. We'd have to do a very good close-up of that to see, but it's not going to be much. The thicker the lens, the greater the curvature of the surface of the lens, the greater the angle between the normal and the incident light, the greater the angle of refraction. So which will bend light more? Lens A. And it all comes back to the nature of refraction. All right? Second question. Which converging lens has the longer focal length? So stop the lecture, go to the quiz, and see what you think. Okay, so which of these will have the longer focal length? Well, the length of the focal length really is telling you something about how far you have to travel from the surface of the lens until light that started out coming in parallel like this gets converged to a point. You can kind of see from this picture, it's going to happen much more quickly with lens A. Lens A bends the light a lot more. It's a stronger lens. A stronger lens has a smaller focal length. It can bend the light sufficiently strongly that that light will converge much closer to the lens than a weaker lens, which will have a long focal length. So which one has the longer focal length? It's going to be B, the weaker lens. we're eventually going to talk about a concept called the power of the lens. This can be a little bit confusing that a weak lens has a big focal length. But we're going to eventually introduce something called the power of the lens, which is the inverse of the focal length measured in meters. And weak lenses will have small powers. Strong lenses will have large powers. That's, I think, a little bit more intuitive, and that's why, for instance, in optometry, people talk in terms of the power of a lens, not its focal length. All right. So let's try a related question. So the greater the curvature of the surface of the lens, the more bending we can make happen. All right? Let's try this question. We place a converging lens in water now, not in air, but in water. What happens to its focal length? Pause the lecture, go to the quiz, think about this a little bit. This is a tricky one. Think about what we just did, maybe even review what we just did, and answer the question. Okay. So now we put our converging lens in water. I'm going to do a kind of close-up of the picture I drew on the previous page. You see our two normals here. You see that we have indices of refraction outside the lens and inside the lens. The material of the lens has an index of refraction larger than what's outside. But what's outside has changed. It used to be air, index of refraction 1. Now it's water, index of refraction, I think 1.33. So let's write out Snell's law, that n1 sine theta 1 is equal to n2 sine theta 2. So here is my theta 1. This is at the first surface of the lens. Here's my theta 2. Because n2 is larger than n1, theta 2 will be smaller. But here's the thing. If this difference between n1 and n2 is very large, the difference between the angles will be very large. If the difference between n1 and n2 is very small, the difference between the angles will be very small. And you can see this do a thought experiment. If you let n1 equal n2, then the two angles have to be equal. The greater difference you introduce between n1 and n2, the greater the difference between those two angles. So in fact, by putting this lens in water, I'll decrease the amount of bending. So this actually decreases the amount of diffraction, or not diffraction, of refraction. Again, resulting in less bending. That less bending means that these converging rays will take longer to come together, and I will get a focal point that is actually longer than it would be in the air. So, a couple of takeaways here. If I want to play with the strength of a lens, I can vary two parameters. I can vary the curvature of the surfaces, and I can vary the material. Both the material the lens is in, but also the material the lens is made out of. All the reasoning that we just went through also applies to the lens itself. If I have a lens made out of a material with a larger index of refraction, it will be more capable of bending light. So the material of the lens actually matters quite a bit, as does the material the lens is suspended in. Okay. So, this is how lenses work. They work through the refraction of rays at the surfaces, both surfaces of the lens. That refraction isn't equal on the two surfaces because the normals are not equal. In this picture, normal 1 here is not the same as normal 2. They are not the same angles. And so the ray it's not like it's reversed. It goes through one surface and the second surface undoes what the first surface does because these are two different kinds of curvature. If this were a flat plane, then that would kind of happen. So if we had just a flat slab of glass, and I had light coming in like this, I should try to draw that a little bit better. So I have light coming in like this. Here's my angle of incidence. Let's say it's made of glass, and so the angle of refraction is going to be smaller. It's going to get bent like that toward the normal inside the lens. It's going to come over here, hit this second area, the second surface. Now the normal at the second surface is the same direction as the normal at the first, and so it will actually end up coming out at the same angle it went in it at. It'll just be shifted a little bit, because Snell's equation works the same here as it does here. Not true for a lens because the normals are at different angles to one another at the two surfaces. Okay, so let's think about lenses. Let's think about converging lenses. And let's imagine this situation. Let's say we have an object that's outside the focal length of a converging lens. So that is the situation that we are specifying. Which of the following pictures best represents what's going to happen to light emitted by that object? Now, again, we're just picking out two rays out of the many rays that this object is emitting. These are just two of them. We can draw many, many more, but they should give you some sense of what's happening to the light that's coming off that object once it passes through the lens. So, think about this question. Pause the lecture. Get yourself a cup of tea. Ruminate on this a little bit. Look at these images. They're in the quiz. And let me know what you think. Which of these pictures best represents what's going to happen to the light? All right, go to it. Okay. So, which picture do we want to select? Well, we can eliminate some. A is kind of wonky. What else can we eliminate? Well, we could eliminate C. Why? Because if the object's outside the focal length, the light that goes through the lens should not end up being parallel to the principal axis like this. This is actually an object at the focal length. So C is a picture of an object at the focal length, or the focal point. So it's not C, although C is an actual depiction of what could happen to light from an object passing through a converging lens. B, again, could happen, but this would be about an object that's, inside the focal length of the lens, or inside the focal point. So this is an object that's too close to the lens. The lens can't bend the light enough to make it converge. That's an indication that we have an object that's too close, that's within the focal length, inside the focal point of the lens. That's actually the same for D. In fact, the object in D is even closer. Oh wait, D doesn't even make any sense. D would be what you would get from a different kind of lens. The answer we're going to come up with is E. If an object's outside the focal length of a converging lens, it's far enough away, the light is entering the lens at a shallow enough angle that the lens can reconverge the light on the other side, and that's when you're going to create a real image over here. So as long as you're far enough away from the lens has the power to bend the light, converge it to a point, not necessarily the focal point. In fact, it won't be the focal point unless you are very, 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 very far away. All light coming into a lens is not converging on the focal point. It will be converging on lots of different potential places. Only light coming in from very, very, very far away gets converged on the focal point. So only if this is my really badly drawn converging lens, it's only light that's coming in from a very distant source. The rays are parallel to the principal axis. that gets converged onto the focal point. Rays hitting the lens at any other angle will not be converged on the focal point. In fact, as you bring the object closer, the image will move away from the focal point because it now takes more work for the lens to bend those rays back down to the principal axis. Okay, let's try another one of these. So this is this one. What about a diverging lens? Let's say we have an object inside the focal length of a diverging lens. Which of these pictures shows what will happen to that light? Pause the lecture, go to the quiz, let me know what you think. Okay. Now, diverging lenses are complicated in some ways. We're going to see that in a minute. In other ways, they're not so bad because the light passing through a diverging lens always diverges. And it always diverges more than what it was doing before. So D is going to be the right answer. If the lens weren't there, the light would just be continuing on these paths. What the diverging lens does is bend it outward, away from the principal axis. Always. Doesn't matter where the image is. The image can be very far away from the diverging lens. It can be really close up to the diverging lens. The diverging lens always does the same thing. Bend the light out away from the principal axis. It's very convenient in that way, and very thoughtful of it to do that for us. Okay, so hopefully this has given you a kind of overall sense of how light interacts with converging and diverging lenses. Let's go into a little bit more detail. In fact, let's try a concrete example. What I would like you to do is pause the video, go watch a demo. I will put the title of this slide near the demo so that you can identify which one to watch. What's going to be happening is there's going to be an image of a bulb, very much like the bulb you saw in the demo last time, not created by a mirror this time, but created by a lens, a converging lens. So this is going to be a converging lens creating this image. That image will be projected on a screen. First, go to the quiz. Make your prediction. What do you think is going to happen to that image? What do you think the image will be? Inverted, upright, or tilted? Then watch the demo, see if your prediction was correct, and then come back here and we'll talk about it. Okay, I'm taking a sip of tea. So what you got to see was an image that was inverted. It was upside down. Exactly like what we saw with the convex or the concave mirror. Why? Well, the very act of projecting this thing on a screen means it must be a real image. So we have a converging lens that is producing a real image. And like I said last time, all real images are inverted. That's a one-to-one correlation. All real images are inverted, all virtual images are upright. Just happens to work that way. So if you project an image on a screen through a converging lens, you will have an inverted image. How do we know it's a real image? Well, real images are the only images you can project on screens. To project something on a screen, what you need is the light to converge at a point on that screen so that that point looks like a point on the object. So if you can do that, if you can get light to converge on that point on the screen, and then it will be reflected from the surface of the screen, like this, it'll look to someone like the object is actually being represented up on the screen. So real images are the only kinds of images that can be projected on screens. When the screen is removed, so let's say we take the screen away, will there still be an image? You don't have to go watch the demo again, but do pause this lecture, go to the quiz, and give me an answer. What do you think is going to happen? If you take the screen away, will there still be an image? Okay. Well, let's think about this topic. Will there still be an image? Yeah, there will be. The screen only intercepts the image. The screen doesn't create the image. The image is still there. The real image is still there. It just isn't being intercepted. It's actually like interference patterns that we talked about a little while ago. The interference pattern gets intercepted by the screen, but it isn't created by the screen. The image is intercepted by the screen here. It's not created by the screen. And just to mention this point one more time, because it is important, real images are the only images that can be projected on the screen. If you want to project an image on a screen, you need to converge all of the rays that represent that image onto that point on the screen, so that when somebody's eye focuses on that point, all of the rays hitting it look like they're coming from that point on the object. And real images are such that the rays from the object actually do converge to real points in space. Okay, so let's do some ray tracing. Just like we had our principal rays for mirrors, we have principal rays for lenses, and they're actually very similar. So our first is starting at the horizontal. So we start horizontal, just like we do with the mirrors. Goes through the lens and does one of two things. Either bends toward the focal point on the far side of the lens, or bends away from the near focal point. I know this might be a little confusing. We're actually going to try this with a diverging lens, because that's the one that's a little bit complicated to draw. But it's very much like our first principal ray with mirrors. Second principal ray, through the near focal point, the one on the same side as the object, and refracted horizontally. That's for a converging lens. Or toward the far focal point and refracted horizontally. Again, we'll see that one in practice very shortly. I think a lot of these, it's going to take some practice and some doing to actually figure out what these mean. Last ray, through the center of the lens. Nice and easy. Not refracted at all, actually. The center of the lens kind of looks like a flat slab of glass. And I did mention earlier, if you pass light through a flat slab, it actually it doesn't change its angle. It's continuing to move in a way parallel to the way it originally moved. Okay, so let's try an example. It's one thing to give these definitions, it's another to actually try it. So what you're going to see is me trying it. You will get to try it on your own on the discussion exercises. Definitely do that. It's good, really good practice. I'm not sure what's going to happen next. I think I've animated this one because it is a little bit difficult to draw this on the iPad. But we'll see what's going to happen. Oops, nope. Okay, I didn't animate it. I thought I did. So I'm going to have to do it by hand. All right. So where is the image for this object? We have an object sitting here. We have a diverging lens. You can kind of tell by the shape of it. It's a diverging lens. Where is the image that this object creates? So what you should do is pause the lecture, go to the quiz. Probably maybe print out the handout or print out this slide in the preview slide deck and try your hand at this. See if you can draw this ray diagram for this diverging lens. And then come back. We'll talk about it. So try this out, answer the quiz question. There's a quiz question here. Then come back and we'll give it a shot. Okay, so let's try our hand at this, some freehand drawing. So we've got our three principal rays. We're going to start with this one. Coming in, kind of horizontally, hits the lens. Now if it's a diverging lens, it will appear to come from the focal point on the same side as the object. Again, diverging lenses bend light away from the principal axis. So this light will be bent up and away and appear as if it were coming from this focal point over here. And lenses have two focal points. That's our one ray. Well, that actually helps us quite a bit. There are two options that we can see that could be the image for this object. We can eliminate three. Let's try our second ray. In principle, you really only need two rays usually to figure out where the location of an image is, but I'll draw all three just to show you how it's done. Third principal ray. If it were a converging lens, we would draw a ray through the near focal point that would hit the lens and then get refracted into a horizontal ray parallel with the principal axis. For a diverging lens, it gets a little bit more complicated. What I'm going to do is I'm going to draw a ray like this. And it's a ray such that if the lens weren't there, it would continue to head toward the far focal point of the lens. Instead, it hits the lens and it gets refracted into a parallel ray to the principal axis. It's essentially the reverse of what we just drew. Coming in parallel, bending out. So these are two mirror images of each other, these two rays. And if I'm over here looking at all of this, my eye's going to backtrack this second ray. It's going to look like it came from this direction. So already we can see B is the correct answer. But let me do our last ray, which is through the center of the lens, doesn't get deflected or refracted at all. There we are. That's actually the nicest, easiest one to draw. All three tell us that B is the image of this object. Now, unfortunately, with diverging lenses, there's going to be some backtracking involved. There's going to be some projecting backwards and also forwards, depending on the principal ray you draw. So, good to get a lot of practice drawing these for diverging lenses. They are fairly complicated. Much simpler with converging lenses. Well, let's try this. We could draw ray diagrams. Ray diagrams are a little imprecise. It doesn't take much to make a little bit of a mistake with them and get an answer that's wildly wrong. So we do have our lens equation. So let's say this. Here, let's actually give us some numbers here to work with. Let's say the initial object distance is plus 3.6 centimeters. The focal length, again, it's a diverging lens, which has a negative focal length. That's critically important. I can't lose that negative sign. Minus 3 centimeters. Now, I'm just putting this here so we can check. Turns out that if you were to measure all these distances out after we've done our ray diagram, we would find that the image distance is minus 1.6 centimeters. Minus because it is a virtual image. It is on the same side of the lens as the object. If you were over here looking and you tried to reach out to get that image, your hand would bump into the lens before you could get there. That is a sign of a virtual image. So let's try this. Let's try actually using these numbers and coming up with something. So I'm going to move to the next slide. I don't think the numbers are here, but let me actually write them up in the corner here so we can use them to do some calculations. So our object distance was plus 3.6 centimeters, as our object distances will always be positive. Our focal length is minus 3 centimeters. It is a diverging lens. And let's just leave it at that. Let's actually check to see what is the image distance. Well, I'm going to use that shortened equation that I talked about in the last lecture, and if you wanted to see the derivation of it, you could have. I made a special little video about that. That the image distance is equal to this expression, the object distance times the focal length over the object distance minus the focal length. All right, let's plug some numbers in. What do we got? We've got an object distance of plus 3.6 centimeters, a focal length of minus 3 centimeters. That minus is really, really, really important. what is our object distance again? It's 3.6 centimeters positive, and then minus a minus 3 centimeters. Cannot get rid of those negatives, cannot forget them. If I do all this correctly, I am going to get my 1.6 minus centimeters. All right, great. That does match what we see on the ray diagram that we created. Let's think about the magnification of the lateral magnification of this image, minus the image distance over the object distance. Well, what is that in this case? I have a minus, and again, I have to preserve all of my negative signs. The image distance is minus 1.6 centimeters. I can't lose that minus. And the object distance is plus 3.6 centimeters. The two negatives in the numerator will cancel out. I'm going to get a plus 0.44. Well, let's go back and see. That plus tells me it's upright, which it is, and it's about half the size of the original. Is that true? It's upright. And it is roughly a little less than half the size of the original. So the numbers work out. They're much more reliable than ray diagrams. Ray diagrams, like I said, can be really tricky. So here's what you're going to do. You're going to go to your discussion sheet and you're going to get some practice with both the ray diagrams and the numbers for diverging and converging lenses. I think you'll find converging lenses are a little bit easier. That's why I wanted to do the diverging lenses here. But go ahead and get that practice. Lenses, I think you can master without too much trouble, hopefully. People seem to do okay with them. And I will see you next week. Have a good weekend.